In this video, we will talk about the second order Euler method, or in other words, the modified Euler method, as well as Runge-Kutta methods. So the Euler method was discussed in the previous video. We used the slope at time 0 or at time I to extrapolate by taking a tangent line here from ti to ti plus 1, and we set that slope equal to the slope calculated by taking yi plus 1 minus yi divided by the interval, or the time spacing, the time step h, or delta t. So a more accurate estimate would be if we take the slope in the middle to be equal to this. That would be the midpoint rule. But here we are using the slope at the left point, because that's the point where we know the value of yi. So as explained in the previous video, this is a first order accurate estimate. As you can see, if you are integrating an exponential function, for example, like the differential equation dy by dt equals y, y is increasing like that, and the slope is also increasing. So by taking the estimate here on the left point, we're underestimating the true slope, which is higher, as we can see here. A more accurate way to estimate the slope is the modified Euler method. In the modified Euler method, we use the average of the slopes at ti and ti plus 1. So that expression is symmetric. So if we look at the slope here and the slope here, and take their average, and then set that equal to yi plus 1 minus yi divided by the interval h. So you might expect that this would be more accurate, because we take into account the average both at the left and the right point, and so we're not going to have this underestimation that we discussed in the previous slide. Another way to derive this equation is to use the trapezoidal rule. So remember, the equation we're solving is dy by dt equals f. If we write this as an integral equation, we're going to have yi plus 1 equals yi plus the integral of f of y and t dt, and that integral we can calculate it by calculating the area under the curve from ti up until ti plus 1, and that integral can be calculated using the trapezoidal rule. So the area under here is equal to, according to the trapezoidal rule, is equal to the small base plus the large base of the trapezoidal times the height of the trapezoid divided by 2. So again, this is the area of the trapezoid that shows up here. So whether we derive this formula using the average of the slopes, or we do it using an integral and using the trapezoidal rule, we get the same result. The problem here is that this evaluation of the slope at time I plus 1 involves yi plus 1. Remember, dy by dt is equal to that function f of y and t. So here we'll have f of y I plus 1 comma t I plus 1. So the value of the quantity y at I plus 1 is not yet known. And that means we have yi plus 1 showing up in both sides of this equation. Because it shows up on both sides, that equation is called implicit. Whereas in this case, we can calculate the future step, I plus 1, based only on past quantities, yi and ti. So this equation here is explicit. So how can we deal with this problem? There are several ways. So one way would be if we have yi plus 1 showing up here as well as here, we could simply iterate this equation. So we could make an initial guess for yi, possibly use the old value or an Euler value like this one. So we would make an initial guess for yi, then use that expression to evaluate yi plus 1, take the new value, plug it back in here, evaluate this expression again, and find a new value, yi plus 1, take the new value, plug it back in here, and so on. So this would be a for loop. In each time step, we would have to do a loop and evaluate y plus 1 in this way. Hopefully that iteration will converge. That's not always guaranteed. It depends on the system we're solving and on whether the time step is small enough. And that's called the self-consistent field method, or the self-consistent iteration method. Now, obviously, doing this iteration is going to cost more time if we have to do it at each time step. But there is a major advantage to this. So the advantage of this formula is that it's time symmetric. So as you can see, if I swap ti for ti plus 1, then this term stays the same. This term would change sign because remember h is the difference between ti plus 1 minus ti. So this term will just change sign, and then these terms will swap. So in the end, if I take this term to the other side, I get the same formula. So that means the formula is time symmetric. In other words, if I use it to integrate forward in time and then use the same formula to integrate backwards in time, I'm going to end up in the same place where I started from. And this is very important. And in practice, this means that if I try to integrate a Hamiltonian system or a conservative system, then energy would be conserved. Unlike this case, this explicit method, the Euler method, for example, if I swap ti with ti plus 1, these terms will change, this term will change sign, but this term will become f evaluated at I plus 1, which is not the same. Unlike this term, which stayed the same under time reversal. So that means if I use this equation to integrate forward in time and then use it again to go backwards in time, I'm not going to end up at the same place where I started from. So I'm probably going to violate some conservation properties of the underlying differential equation that I'm trying to integrate. So, for example, energy is not going to be conserved if I use an explicit method like that. And volume in phase space for a Hamiltonian system is not going to be conserved. So we're going to violate Liouville's theorem and so on. Whereas these quantities, so volume in phase space and the energy, are going to be conserved if we use this time symmetric formula. Now, what happens if we don't want to do the iteration? Well, one thing we can do is to turn this formula into an explicit method. We can do this by doing the first iteration that I just described and stopping there. So, for example, if I take the Euler step here and use that to estimate the future value, and then do that only once, then I can construct a formula from that one substitution. And that's going to be higher order than h. So let's see how this can be done. So let us summarize what we've discussed so far. The Euler method is a first order method. The first step of the method is simple. It just uses the slope at time t0 to evaluate the quantity yi plus 1 minus yi divided by h. Okay. The first step of the modified Euler method is to use the average of these slopes at ti and ti plus 1. And then what that does means we'd like to set y plus 1 equal to yi plus this average of the slopes times h over 2. But as we just discussed, we can't directly estimate the slope at yi plus 1, which is needed. So instead, we can do an approximation here. So the approximation is to do an Euler step, use the Euler method, and set the result equal to y star at I plus 1. And then use that Euler estimate to estimate the future value here in this symmetric formula. So instead of using the exact value of yi plus 1 here, I'm going to use an approximation to y plus 1, which is obtained using the Euler step. Now, in doing that, I have created an explicit method, because here yi plus 1 star depends only on the past. And of course, ti plus 1 is equal to ti plus h. So we have converted an implicit formula, which we had here, to an explicit formula here. But there's a price we pay. The price we pay is that now we have broken the time symmetry. So again, if I change ti to ti plus 1, this formula is no longer symmetric. So it's not going to conserve energy or simple electric structure for Hamiltonian systems. So it will not conserve area and phase space. It will not respect Wheel's theorem and so on. But the advantage is that it is explicit. So now we don't need to do a loop in each time step to iterate and solve for the future step. We can just calculate the future value yi plus 1 immediately by first evaluating this quantity and then plugging that into here and evaluating this quantity, and we get the next step. And we hope that if h is small enough, then that approximation will be accurate enough for practical purposes. Okay, so now the question is, how accurate would that be? So for a single step of size h of the modified Euler method, the error in the approximation is of magnitude for order h to the third power. So one step of the modified Euler method is third order accurate. However, the error accumulates as we add up several steps, because we go from yi to yi plus 1, and then from yi plus 1 to yi plus 2, and so on. So if we integrate over a large interval and split that interval to many time steps that are equal to h, then we pick up an error of order 1 over h. So that's the order of the number of steps. So we have the number of steps times h to the third. So that's h to the third divided by h. So overall, it's h squared. In other words, when we integrate over some interval using the modified Euler method, the order of the error is second. So this is essentially a second order method. And if we recall from the previous lecture, the simple Euler method had an error term that was of order h. So again, the Euler method is linear in the time step, and the modified Euler method is second order accurate in the time step. Okay, in practice, we may code up the Euler or the modified Euler method just to get familiar with how to implement a simple numerical method. But we wouldn't really use it in practice if we want to get a more accurate solution. We would want to use a higher order method with higher accuracy. A wide class of such methods are the Runge-Kutta methods, and perhaps the most widely used is the fourth order Runge-Kutta method, known as RK4. This uses a weighted average of 4 slope estimates to make each step, and it's an explicit method. So let's see how that works. So again, we're solving a system of ODEs, or a simple ODE of the form dy by dt equals f, where f depends on y and t, where t can be time, or it can be radius, it can be anything. And then to calculate one time step from t to t plus h, or ti to ti plus h, we calculate these quantities over here. So these are essentially slopes. So first we calculate the slope at ti and set it to equal to k1. Then we calculate the slope in the middle between ti and ti plus h. And we do one evaluation, k2, and then we use that k2 to do another evaluation in the middle. So we do 2 evaluations in the middle. So remember, k1 is calculated here and plugged into here, and then we use that to evaluate k2, and then k2 is computed here and then substituted into here. Then we use that expression to evaluate k3, and then finally we plug in that k3 into this expression and evaluate that slope at time ti plus h. So that's the next time step. So each of those is an estimate of the gradient of the function, and then we combine these terms in such a way that the result is fourth order accurate. So you can see that the result looks like this. So that's the time step, and then we take 1/6 of these terms. And these terms are weighted. So each of those is a slope estimate, and the terms in the middle are counted twice. So they have twice their weight. So overall we have 6 slope estimates, so we average that as 1/6. Now this formula may look symmetric, but it's not. As you can see, it all depends on yi. Everything else is calculated based on yi and ti, all of these estimates. I'm not using the future value anywhere. So these steps can be calculated explicitly one after another without any iteration. So this is an explicit method. Because it's explicit, it's not time symmetric, it's not going to conserve energy, but it's going to be fourth order accurate in h. And so for most practical purposes it is good enough. Not always, but it is very popular because it is sufficiently accurate. So usually fourth order accurate can give us many digits of accuracy. So we will see that in practice when we code up a few examples. Okay, so again, as I just explained, these are 4 slope estimates, and we can think of that as a slope evaluation here at the first point ti, a slope evaluation in the middle, another slope evaluation in the middle, and then finally a fourth evaluation at the next point, ti plus h, or ti plus 1. And the Runge-Kutta step is a weighted average of these 4 slope estimates. So one Runge-Kutta step looks like this, and it takes you from time I to time I plus 1 by doing these intermediate evaluations. Now, the weights in this sum have been chosen so that the terms cancel out when we consider a Taylor series expansion for the overall time step. There is a whole family of methods with different weights and with different numbers of substeps. So in this case, for the RK4 method, the terms that depend on h squared, h cubed, and h fourth, they vanish. It's been constructed to make them vanish. So for a single step of size h of the RK4 method, the error in the approximation can be shown to be of order h to the fifth if the time step h is small enough. And as before, the errors add up because we estimate yi plus 1 from yi, and then yi plus 2 from yi plus 1, and so on. So there is an overall error term that we pick up in each of those time steps. So after n time steps, we're going to have a factor of 1 over h increase in the error. So overall, the error is going to be of order h to the 4, so the method is 4th order accurate. You may find more on Runge-Kutta methods on the book Numerical Recipes in C++ by Press and others. This book also covers adaptive step size. We're not going to use this, but sometimes it can speed up the computation. So the idea of adaptive step size is that in some regions the variables are changing rapidly, so you need small time steps, but in other regions the variables don't change much, so a larger time step is okay. So adaptive step size methods control the time step by looking at the error and how much terms are changing. We're not going to use that in this class, but you may want to look at it in the book, which you can find online if you're interested. That's all for this video. Thank you for watching.